Welcome once again. I will talk about how we can use vibration and shock field data for lifetime studies. And let us start with this. So here, I have an agenda. I will make an introduction and why we do this kind of work here. And of course, introduction of the company, the project, and myself. We will look a little bit into how vibration and mechanical shock data can be looked at and analyzed. We will see field measuring of vibration and shock, and we will have some actually cases in this here I can present results of. Then I will make introduction to acceleration models and accelerated life testing, and we'll end up with how do we come from accelerated life testing to an estimate for the life at the use stress level by using what we call a mission profiling. And then we will have time for questions in the end. Let's go on. The company I work in is called Force Technology. It's a technological service providing institute, and some of the services are testing where I am working with. It's a part of Danish advanced technology group called DTS in Denmark. It's a kind of self-governing and independent institute. So we are not owned by any shareholders or by ourselves, but we are independent, and many activities we do can be done in an accredited according to international standards. We have offices, the main offices in Denmark here, but we have offices in 6 different continents to the world. And I have the pleasure of working with more than 1,000 skilled colleagues in this company here. When we have this, what we're presenting here today is a part of what we in Denmark call a performance contract, and we call it long-lived products. It's an ongoing project, so we are not final yet. It's led by my colleague Susanne Otto here from Force Technology. We have several project partners, both from industry and from university, and we're very pleased of that. And it's funded by the Ministry of Higher Education and Science in Denmark. And what we see over here is you could call it a wheel of the circular economy, and we will work something with the design. How can we do good designs? So we have sustainable design. We can have something, we are working with technologies and methods to evaluate how is the condition of products for the moment, and if needed, can we find methods to make lifetime extension. And finally, some of my colleagues are working with and upcycling of electronics products, which are far from trivial. From my point of view, you could say that the project here is circular economy for engineers. How do we actually do this kind of stuff? A little bit about myself. I'm a reliability specialist here at Force Technology. Earlier it was called, way back in the past century, it was called Elektronikcentralen, and then it was Delta, and now we are part of Force Technology. I worked in a business unit called Product Compliance, for where we check that electronic product can fulfill the given requirements, and I'm in the team called Engineering. We are the more practical doing practical physical testing. I was educated many years ago, back in 1981, and since that I have worked for more than 40 years with climatic and mechanical testing of electronic products. So the focus here today will be from a testman's point of view, and it will be on electronic products. I have done some conductor of quite many training courses, and I also a part of this, lucky to be a part of this long-lived products performance contract. And actually, I do have a life outside Force, so this is one of the interest. And there's no Photoshop in this picture; it's for real. I guess everyone says that. The motivation why we do this is that when we know how the real life condition for electronic products are, then we can avoid situation where we make the product too weak. We can call it engineering, so the product will fail too soon, or we can make it too good when it lasts far too long. If I'd made like a mobile phone that could last for let's say 20 years, then probably not many people would use it after 20 years because it's outdated. And in the old day, we used to try to make electronic products last as long as possible. Nowadays, in order to avoid waste of resources, we try to find the right lifetime, not too short, not too long, and we want to find it balanced between the different parts of the electronic products. And when we have new technologies and new applications for existing technologies, then we might need updated field data as we do here. If I have a general sequence for how we can work with this field condition, then we can identify the actual conditions, use situation or field condition. We can identify the mechanical strength of the product. We can identify what we call critical failure mechanisms. We can establish one or more what we call mission profiles. That's how is the use scenario. And there will, of course, come example of this during the presentation. And we can use what we call acceleration model to estimate time to failure at different stress level. It can be done both theoretically without having physical objects. We can call it calculation or simulation, or we can do it physical by testing. And of course, we can do combination in this. In this webinar here, we will focus on vibration and mechanical shock. And because I'm a test engineer, it will be from a test engineer's point of view. The critical failure mechanism is something we call high cycle fatigue, and we will come back to the definition of that. And mission profile is load distribution over time. And we have an acceleration model called inverse power law that also will be explained and illustrated. Let's go on. When we have to describe vibration and shock, we can do that in many ways. From my point of view, the most versatile description is to indicate acceleration of time. For instance, if we have a dashboard in a car, we can mount, as we see in the red circle here, some accelerometers, sensors that they can measure acceleration. And in the picture here, we have the larger accelerometers is a 1-axis accelerometer, and the other accelerometer here is a 3-axis accelerometer where we have the 3 wires coming out, and we can measure it in 3 directions at the same time. And for instance, if I start the car in the morning, I will have here acceleration as function of time, and I perhaps let it run in idle for a short time while I fasten my seat belts and things like that. And then perhaps I see like a constant frequency and constant level. But then I start to drive and I eventually hit the curb before going out on the public road. So I get some kind of a peak in this one here. When I go on the roads, I can see some different frequency and perhaps there are some potholes and some small holes. So I will see a more changing image of this one. And if we were in a situation where we had some advanced strength and fatigue simulation software packages, then we could take this time history and put it directly into the simulation model. And for instance, as a passenger on an airplane from time to time, I'm very, very glad that the guys designing the airplanes, they have this kind of simulation too, so they can calculate that the wings nut will drop off, at least not while I'm in the airplane. So sometimes we can do this, and then we are basically done. We have them data from the real world, and we put it in the simulation software, and we're done. But when we look on electronic products, they are made of many different materials. They have a quite complex geometry if you want to make a very detailed computer model of it, and it's a result of many different or several different production processes. So it might not be feasible to make this kind of simulation on electronic modules. And in order to have some calculation and some test and accelerated test, we have to categorize the acceleration time history so we can get on with it. And I will show you some example of categorization. So we have the same time history here. And when we see like one frequency dominating, we can call it sine vibration. Of course, the amplitude can also vary. When we see something with not so high acceleration level, but for longer duration, and several frequency, we can call it random vibration. And when we see this kind of peaks where we hit potholes, and we can call that mechanical shock. And that's not just us at Force calling it. That's the international standards on mechanical and vibration shock testing of electronic products. They use the same terms on this one. I will come back to later on what random vibration is, and we look into detail with that. Because actually, when we have to look and have to analyze this kind of acceleration time history categories, when we have sine vibration, sometimes we can see directly from the time history what is the level and what is the frequency. And we can also make a very simple frequency analysis like FFT or something like that in order to see the frequency content. If we have what we call random vibration, we do something called power spectral density analysis, and I will explain that later on. It's basically a special frequency analysis that is very suitable for acceleration signals. If we have the shock, mechanical shock, then sometimes we have simple shapes in the time domain, so we can see it's a half sine or whatever it could be, and then we can look at it directly on the time history. If it's more complex shapes in the time domain where we can recognize the simple geometrical shape, we can use something called shock response spectrum analysis. Of course, there are also other kinds of vibrations. There's something we call mixed mode. That could be sine on random, that is relevant, for instance, for helicopters, or it could be random on random, that could be relevant for military tanks and stuff like that. Okay, when we want to find some of these vibration and shock data, we can get data in many ways. Three of them are: we can use existing data for similar application and similar products. We can try to get data from international recognized standards. The problem about getting from standard is that they might have included a certain level of acceleration factor, and unfortunately it's not very clear to find a good description of what value give you. But we can also go out and measure, and that's what we will demonstrate in this webinar here, where we have a case with an e-bike and an electric car where we had made some measurements. First, we take the e-bike. So here is my electrical bike with a front wheel motor and the battery in the frame behind the label on it here. And we equipped this one in the basket with some recording instruments, basically hard disk musical recorders, music recorders, some batteries, some acceleration preamplifiers, and then we take accelerometers, one single axis and one 3-axis accelerometer. We mount them by wax, and then we go for a ride and measure the vibration and shock levels. The measuring points we have used on this bike here was where we could have electronic parts. So we have one measuring point near the crank where the pedals are. There's a sensor sensing how fast we are moving the pedals. We have one measuring point near the battery upper end, so we can see what is the conditions for the battery. There's a controller on the handlebar, and that's also a piece of electronics, so we have measured there. We have measured close to the motor, not directly on the motor. That would the setup we had, it would be difficult with the wires turning around the wheel. And then we also had on the luggage carrier, we had an UPS, so we could have power for instrumentation, and we also did some measurement on that. That's not actually the input vibration to this one, so it's not the most important, but it's good to have it, so we can make transportation basically for stuff carrying with bikes. Okay, when we did go into the measuring, there was my colleague Jan and me. We went for a ride, a nice sunny day with the equipment of the bike. We had, like, very important at force, safety moment. So we had both helmets and safety shoes. So everything was okay. And we went driving in a park close to the labs where I'm working in Hørsholm. That's a little bit north of Copenhagen. And we had some of the roads on the green one here is on gravel roads. Then we had some asphalt road. Then we had a small part with paving stones on a parking site. And then we had some curbs driving over, and we went for that ride several times in order to measure the different measuring points. Of course, we need to calibrate the setup, but this year I will not go into detail with that one, but we like to calibrate the whole chain from input to the accelerometer to the final analyzed results. And we use exposures close to what we expect to get, like random vibration, sine vibration, and bump. And now we come to some of the results. So this is, you can see in the top here, you can see a time scale in minutes. So this round trip took about almost 7 minutes to drive around. And we can see the green area here. That's when we are driving on gravel road. The yellow one is on asphalt road. And the red one is on paving stone. And this is acceleration and function of time. And when we had the curbs, you can see some short peaks. That's where we have the shocks. in this one. We have a reference accelerometer mounted on the crank in the entire time, so we can compare the different runs we made with the bike. And then we have the 3 axes from the accelerometer that we move around. And of course, in this setup here, because the measuring point is near the crank, then this curve with the colored boxes should be the same as the reference. And we can also see that on this curve here, measuring driving direction front back, there are some flat points where we don't have any time history. And if you see that in real measurement, you should be suspect that you have some problem. And we had, unfortunately, some sensor cable issues, so we could not measure the entire time. But if any of you guys have tried to make practical measurements out in the real world, you will know that that can happen from time to time. Now we can try to look more into it and look into this, what we call a power spectral density. It's a frequency analysis that gives distribution of power as function of frequency. We can use PSD analysis to any kind of time history with any engineering unit. If we use it for acceleration, we sometimes call it acceleration spectral density. And seen from my point of view, it's the most versatile frequency analysis for vibration, mainly because the y-axis is with absolute units. So we don't have all these, for me, annoying dB scales and reference points. I can directly read what is the level at a different frequency. You can find something called a kind of an average value, a root mean square value. You can find it directly for the time history, or you can be calculated as the square root of the area under the PSD spectrum. The RMS value is good when you compare different levels, but it does not say anything about the frequency content or frequency distribution. That's why we need the PSD analysis. And how we actually do it, or we do it by software, we have the blue input signal here, the acceleration time signal, we put it in here. Then we have a number of bandwidth filters, each with a frequency and a bandwidth around it. So we take the G coming in here, we take it through the filter. We still have G, but now only at one frequency. Then we square the value. Then we average over time. And finally, we divide it by the bandwidth. So we'll have here, we have the unit G, and then we have G squared, and average is still G squared. And then we divide it with the bandwidth. And then we have a value here called the PSD at that frequency. And the unit of that is G squared per hertz. I'm an old test engineer, so I still use the unit G, the acceleration of gravity. Of course, it would be better to use the SI system, and then your unit would be meter per second squared divided by hertz, and that would be a unit called, when you reduce it, it will be meter in squared divided by second in third, and that's a kind of strange unit, so I prefer this G squared per hertz unit. And here's an example how it looks on the, we have taken here the controller in the Z-axis up and down, and we have the different roads, gravel, asphalt, and paving stones, and we can see the spectrum here. So we can see most energy around the 10 hertz. We can see in the small figure up here that, for instance, for the paving stones, driving on those, we had 1.1 GRMS. That's a fairly high level, and you can clearly hear everything rattling on the bike when you drive over this. You can also see on this one here that the shape is basically the same for this one, because even though they have different roads, they are very much influenced probably by the flexibility in the tires and in the handlebar itself. So you will typically see on the same measuring point, the same overall shape of the spectrum, but of course different levels depending on which road you are driving on. Now we go to the example with the electric car. We went to have this in Denmark. We have a lot of these share cars, and we booked one of those. We went on different roads, like gravel roads, and you can see here that's my colleague who has washed the car partly after the rent. It's a dirty job, but someone has to do it. So we went on curbs, we went on asphalt road, we went on paving stones. And as for all kind of practical measurement, you have to be aware of pedestrians and people opening doors. So it's not very easy to do exactly the same speed every time. But that's why we include the reference point. And then we used also gravel roads. Here's one from the woods where there are several potholes in it. It's basically the same measuring setup as we have for the e-bike. If we take some of the measuring points, the first one is what we've always seen before. There's a dashboard in the middle here, an information screen. And the second point was out in the engine room. So we can see in the blue one, here we have the accelerometer mounted on what we call the power electronics. We can see high voltage electrical wire goes into here, and it's directly on the top of the electrical motor and the transmission. That means the drive line for it. We also saw that there was a big fan in the engine room, and there was an electronic calling on that fan controlling the speed of the fan. And of course, because the focus for this project here is on electronic parts, we select measuring relevant for electronics. If we were interested in like springs for the cars, then of course we would measure around the spring. We also took some measurements. It's not easy to see on this one, but it's down on the rigid part of the chassis near the front wheel suspension. And finally, we took the accelerometers and situated on the rear wheel suspension. That was the most dirty point, and we were a little excited to see whether the accelerometer would be kept in place. We attach it by wax when we drive on the roads, and we have this dirty situation, but it survived. So we're glad for that. And when we look into the results of this kind here, then I have a time history here. We can see the timeline. It took about 17 minutes to road this same road here, where we have once again we have a piece with gravel road. We have some asphalt road with different conditions. You can see it; they are in different shape. We had the paving stones, and then we had some curves in the start and at the end where we drove over some curves. And this one is measured in the dashboard in the middle, and this is in the driving direction. If we take some of the other measuring points, and here we are taking the power electronics, so we can basically see the same timeline. It's a little bit different on where we have the break between the different sections because there are different traffics when we are driving around. But what you can see is on the dashboard, you can see that the vibration level is very much depending on the road we are driving on. But when we measure on the power electronics, that's not that dominant. And actually that is because we have vibration in the power electronics from the motor and the drivetrains themselves. So can we say that we always have the same mission for different positions in the car? No, we cannot. It is different. So we will have different lifetime whether we put electronics inside on the dashboard or if we put the same electronics on the power electronics. So we have to adapt to the local vibration level. Here I have chosen to take some of the recorded shocks. That is where we have measured over the curbs. When we have this measurement for the electric bike, it was like 6 minutes, and the car it was 17 minutes, and we have 5 measuring points in each, and we have 32 kilohertz of sampling rate. We have a huge amount of data, and we're still digging into all this very interesting data. But I have taken some extracts here for you. So here we have acceleration as function of time, but we have on zoom on it. So the first curve here is the curve is from the rear wheel suspension in the Z-axis, and you can see that we get up to values of about 10 Gs and some duration here. We have the time in seconds. So the duration down here is at some 20, 30 milliseconds. And we can see a very nice typical, like a half sign when we start up, and then we can see a decay. And actually, you can say on this one here, it seems like the shock absorber is working good, because once we have a disturbance, the decay is fast and the shock absorber is working. When we look at the same time and look inside on the dashboard or in instrument board inside the car, now you should note that it's a very different scale. It's a factor of 10, more zoomed in. And you can see on this one, we barely have a half G, less than a half G, but we have a much longer duration in the order of a quarter second or half second. And that's actually showing that the suspension of the car is working okay. You could also say in this car here, not speaking bad about this car, but the instrument in this car is actually a little wobbly. In Danish, we said it's a piece of dilladalla. But that's good for the vibration level, because then we get smaller vibration. So as long as it doesn't break off, it makes protection for electronics inside. So once again, we cannot say that the shock in a car driving over a curb is this value or that value. It's depending on which point we are measuring on. A little bit about shock categories. We can have this where we have a simple pulse shape in the time history. It could be a half sine, it could be a sawtooth, or it could be a trapezoidal. And we talk about the acceleration, the peak value, and the duration of the main pulse. And sometimes we can find these kind of data. And if you look at this one going back, here we can see some half sine and some sinusoid. Here it's not easy to see what it is. So when we have more complex pulse shapes in shock, then we, like this example here, is taken from an IEC standard. Me as a test man is very fond of this 60,068-2-XX, and -57 here is for shock response spectrum, and you can use that as a good reference. And then you can calculate for a given time history in acceleration as function of time. You calculate basically how much will different resonances respond to this shock you put, and then you plot the maximum value as function of the resonance frequency that you look into, and you plot it as an acceleration at different frequency. That's a very short about shock response spectrum, but it's a good way to analyze the frequency consent and get a good axis where you can read directly the correct acceleration value. So if we don't have access to all these advanced software, as I told in the start, where you could put it directly into simulation and calculate stress and fatigue, then we have other possibilities. If we know the strength of the product in terms of time to failure for a given stress level, we can use the acceleration model and assume some parameters, and then we can calculate the time to failure at another stress levels. And that could be the stress level due to the field data low, as we just show some examples on. If we don't have the strength, we can do a test where we find the stress, the time to failure at one stress level only, and then we select a model and we assume some parameter, and then we can calculate it. If we don't have the acceleration model, or we don't have the relevant parameters for it, then we can perform what we call an accelerated life testing study. And then we test several specimens, the same product but different samples at different stress level, and then we find time to failure for each stress level. And when we analyze that, we can find a suitable acceleration model, and we can find the parameters for it, and then we can basically calculate time to failure at any stress level. But remember, we have to be in the range of the same failure mechanism. We cannot, if we had make a test at a certain level, we cannot extrapolate the values to very, very low vibration level or very, very high vibration level, because then we will change we will change failure mechanism, and then the results are not valid anymore. The acceleration model is a mathematical model with a relation between stress level and time to failure. It's connected to or valid for a given failure mechanism. That means that we have different acceleration models for different failure mechanisms. Is that annoying? Yes, it is, but that's the way it is, unfortunately. And we have to find one or more parameters for the acceleration model for the actual situation. Before we go into the acceleration model for what we call high cycle fatigue, we will look into something we call the stress strain curve and the SN curve. The stress strain curve, we plot stress in a pin that we can either bend or pull in, and then we measure the relative elongation of it, we call that the strain. And in the first area here, we say we are in elastic range. I'm not sure whether you can see something on my camera right now. Here I have a small beam. If I do like this, a smaller deformation, and I let it go, then it will come back to the original position. But if I make a big deformation like this, then you can see that I have a permanent deformation, and that's what we call the plastic range. And some of you that are very familiar with mechanical strength calculation will know a lot of details of this one here. Here it's important to distinguish between elastic range and the plastic range. If we do like something we call the SN curve, and SN is simply stress as function of number of cycles to failure. It's also called a Wöhler curve, and it could be made with a very simple. It's like here we're testing a rod, the blue one here, and we have a motor turning around, and we have a load here in the end, and due to the gravity, we will inside here at that point when we rotate the bar, we will have a stress that is making a sinusoidal movement. And then we can apply different masses, and then we can measure, sit and wait and see how many cycles will it take before break, and we can plot it. We will see this kind of scattered plot. If we look at more in general, it could look like this. At very low number of cycles, we have what we call the ultimate strength. At very, very high number of cycles, we have what we call infinite life or the fatigue level. But in between, we have some relation between number of cycles and the stress levels. So once again, we have here the elastic range, and because we need many cycles, like from 10,000s up to millions in order to have break here, we call it high cycle fatigue. When we are in this area where we have the plastic range, it's could be from 100 up to 1,000s, and we don't have a very strict value here in between. We call that low cycle fatigue. And because the slope of the curve here can be different, it's important to distinguish. So when we look on this curve here, we can see the smaller stress, the longer lifetime. And that's basically when we try to use the acceleration model is to find the formula for this line here. And that law we call the inverse power law. And this is one of them. We have the use stress level, S use. We have the stress level during a test. It could also be at two different use scenarios or two different test scenarios. And then we have the life in terms of time to failure for the use level and the test level. And you can see here that the use and test are switched around. That's why we call it inverse. And we see that the stress level is raised in an exponent. And that's why we call it inverse power law. And that's a good choice, a simple formula, a good choice for many mechanical conditions. Not for everyone. And then those of you guys who knows a lot about acceleration model will know that there are many, many different acceleration models. Then we have to find this M factor. It's connected with the slope of the decreasing part of the SN curve. If some people use like big M, it's from high cycle fatigue testing of simple material mechanical parts. The drawing down here is from the test set Force has at Linux, where we can test. You can see the size of a container and a small man, where there we can make mechanical high cycle fatigue testing of very big mechanical parts. We will also here in this webinar use the term M average. That's high cycle fatigue average value for complex product like electronics. And we will use a small m for a low cycle fatigue value for a specific failure mode. People are not using these terms consistently, so it's okay whenever you see an M factor, you ask, what is this one relevant for? And let me show you where you can find some value. We have something called SPM Reliability Management, and they make reports. Luckily, we at Force are often involved in this, but also Danish industry is involved in this. And this one here, SPM 179, we can find typical M vectors for the mechanical parts, and here you can see different materials like steel or brass or fiberglass, and you can see M values in the range from 10 to 20, sometimes a little lower and sometimes a little higher. When we look in this little m, here is a list from electronics, and the stress is thermal shock. Then you can see, for instance, for different solder points, what is the M factor for that? And it's typically in the range from 1 to 3. And we look at this average value for electronics. We can look at the next slide. And here I have mentioned a reference called 6 in the bottom here. It's a document from an organization called Zoe, and they have on their website, you can find this handbook for robustness validation of automotive electrical and electronic modules. It's free of charge to download it, and I can very much recommend it because they have a big very much information on this subject here. And here we can see from this one, we have can find different values. So for instance, they say for complex electronic units, it's somewhere between 4 to 3, and recommended value is like 4. For some other sources like sine or random complex, it's somewhere between 5 and 20, but that's based on the rotating beam data. And that's not, we don't see much electronics that is a rotating beam. A recommended value for complex periodic variation of any module and random vibration here is like 8, and recommended value for sine vibration of hardware is in the order of 6 here. So we can see something where between 4 and 6. And does that have a huge impact on which value we select? Yes, it does, but we still have to try to find a reasonable data. If we don't want to use these typical values, we can try to find it because we just have to do a test where we test to failure at different stress levels, and I put in just because it takes time, and it's and takes time is equal to cost money and resources to find good data on this one. And there are many different methods you can use in accelerated life testing. One of the methods is called calibrated accelerated life test. It's defined in GMW standard. And from my point of view, the benefits of this one is that you actually can get a reasonable amount of confidence on the results with a limited number of test specimens. Ideally, we should have hundreds of test specimens, but that's not very often we can get that. And then we have, with this method, I will not come into details, we have control of total test time. So we can plan that we will maximum use like 2 months or whatever it could put to our lifetime study. But I will show a typical an actual graph that can be from such a test. It's from another SPM report 181 here. And here we can see life as function of force on a construction. It's in the unit of newtons. You can also see that this was for a special system where we run electrical current constant at 20 amps, and then we change the force, and then the different colored dots are from the different stress level. And on this one here, if you look in the corner up here, you can see that on this one here, we use the inverse power law, and we use something called a Weibull distribution function to fit the data. Weibull is one of many distribution functions. It seems to fit. It's a very flexible one, and it's a good first choice for many physical data from testing. But you can use normal function or log normal or student or whatever you would like to use. So now we're getting closer to the end. We have an accelerated lifetime, and now we have wanted to find what is life at the U stress level. And once again, the testman likes standards, and in this one here we have the standard IEC 62506. That's methods for product accelerated testing, and in this one, a type B testing is called a quantitative accelerated test. That's where we work what we have talked about here with cumulative damage. There's also a type A test called actually qualitative accelerated test. That's kind of a robustness test. That's test where we identify the weak points, but we don't get any idea about lifetime. So type B testing is what we use here. We have to find an acceleration model for high cycle fatigue, this with small cracks getting bigger and bigger for each stress level. We use this in inverse power law. In this example for this standard here, there are some good examples. It's not a cookbook for every test you do. It's methods that is described, but there are some good examples in it. And they recommend in the examples they recommend to use M equal to 4. From this other source we saw just before, we saw something between 5 and 8. And what we actually do here at FORCE is that when we make the analysis, we do it with different M values. Then we get an idea of the range we are working in. And then as input to the model, we need this mission profiling analysis. And there will come a little bit more on that. And then we can accumulate damage from different stress levels during use. We can calculate to one stress level by use of the acceleration model and the parameters we have found. So if you want to know more about mission profiling analysis, the TWI handbook I have shown before is also a very good source. But in the SPM, we had made a report with product mission profiling where we have some practical examples how you could do this. But for instance, for the bike and the electrical car, we need to say how many years do we have in useful life, how many driving hours per day, on what kind of roads, how many curbs drive over per day, and other stuff. And what about the user? Are we looking for average value, or are we looking for what we call the severe user or the extreme user? If I look on bikes in my family, my bikes seem to last very long because I'm old man driving carefully. When I give it to the kids or the grandchildren, they won't last for more than a year. Then they are more or less totally smashed. So we also have to consider what is the use scenario. And this one actually shows that in the old day, we tried to make like one mission profile that was the true. But of course, we can see on this one here, it's not a one situation. And then you will say, but then we have different lifetime with different missions. Yeah, exactly. So nowadays we typically set up a number of mission profiling scenarios. So to sum up on this one here, I've shown some how we can use this field data. We can use that as input for lifetime studies. The principle is simple, but I must say that we have to do and take a lot of decision, and they are hard to take. You don't know. It's not always easy to see what is the consequence if I go this way or that way or take that value or that acceleration model. But my advice could be then take some of the different one and see what order of magnitude are you working in. And then something about actual acquisition of data. It takes time, and you have to have the right equipment, the right personnel, the right occasion. If it's on a train, or you must be there when it's possible to get in the train or in an aeroplane or a car. And there are practical issues when we sample data. We saw here with the bike where we had an electrical cable. When we did the car measurements, then one of the batteries ran out of power towards the end of it. So if people say they have made a big measuring program out in the real world, and they say that they don't have seen any practical issue, I will not say that they are lying, but perhaps they're forgetting that they did have some problems. And all this sum up to that a large amount of engineering judgment is needed. Engineering judgment is something we use in the test world, and it's another term for use your head. Look into it and see what is reasonable from the knowledge and the experience I have. And a good proposal is to sometimes to step back. When you dig down to data, you can get blinded by the amount of data. And for instance, for these just a few measurements on the car and the electric bike here, we have several gigabytes of very interesting data. Take your time, step back, and take an overall view and make use of engineering judgment, common sense. But I still recommend it's better to do something than nothing. And I like quotes, so I have this final quote here. That will be, all models are wrong, but some are actually useful. So I hope I give you some illustration on how we can use this field data for lifetime studies, and I hope you have got some inspiration on it. Okay. Do we have like some? I cannot see the chat from where I'm sitting here. Are there questions or comments?
There are a lot of applauses, but
okay,
David Richardson, yes, thank you, have asked the question: how are you verifying the data are stationary and ergodic, meaning well representing the whole, to ensure the PSTs are valid during your testing?
I look at the data generally, and if there are changes where I can see that it's not for PST, we typically use the normal distribution of the acceleration. And if I see there are difference, I basically split it up and I say I have one situation where I have that PST and another situation where I have the other PST. So you have to look into the data. I've not seen anyone being able to do that automatically. So you have to use your engineering judgment, look over the data and see what is the difference. And for instance, we saw on the car, we had 3 set of measurements on asphalt roads, but they were a little different because the condition of the roads were different. I think one good advice is advice is to whenever you go out and measure something in the real world, it's just a sample in time and place and condition. So if you want to find the full truth, you have to measure continuously, and you will never get done with all the analysis. So make some representative samples, use them, and take care of not saying that's the full truth. I hope that answered it.
And thank you, Kim. Andreas Bovin is asking, is the derived acceleration or jerk relevant for the lifetime estimation?
Yeah, it can be in some circumstances, definitely. And for you who are not aware of it, as you can you can difference position in millimeter to velocity, and you can differentiate against to acceleration, then you can different also to jerk or changes in acceleration, and that can also mean something. But once again, you have to look into your failure mechanisms and your failure modes in the product to see what is important in this one here. My point is that you will get quite far with acceleration, but you cannot say that in any case you can neglect the jerks.
Thank you very much. And now it's the last chance to ask questions. Oh yeah, and Jan Gårdsvig Nielsen asked, have you seen a practical use of the method that you can point to? And have you tried to let your grandchildren use your bike and repeat the measurements if you dare? Does he know your grandchildren?
No. So he will know that I would not dare. Oh, of course I would do that. But
Okay.
that's very important to see it, and it's a very relevant question. And you have to consider. We call it there. We saw, is it the average, the extreme, or the severe? And we have to do that for different uses. As a little example, I can say that, for instance, Bosch, they do a lot of electronics for e-bikes. And when you buy a e-bike with some Bosch equipment, you got the possibility to get an app where you can be connected to a Bosch e-bike community. And there they would ask you to get permission to not know where you have been, but they know how long time have you been on your bike, and perhaps they have some information of how you use the bike, and because they can see the velocity. So, for instance, slow velocity and short intense period, it might be a mountain bike running at steep slopes. So they try to get this mission profiling data from that. And we see more and more our customers actually measuring condition during use. And we, of course, everyone has to be aware of these GDPR rules, but that's a very good way to get data.
Thank you. And another question from, I'm not sure if I get the Finnish name right, Juntunen Markku. How do you verify shot data?
Basically, we record it, and then we do the SRS analysis. I have not shown any of the actual one here today here because I had to limit the amount of data that I could have in 1 hour. But we do the SRS analysis, and the SRS analysis is a very good way of comparing different shocks. And then I can compare from real life to testing if I want to that, or I can do from different shocks in the real life and compare them. Then I have to know some information of the resonances of the products. And for a mechanical test guy like me, I do a lot of time, use my time to measure resonance in product, because once I have resonance in the product, a new product, then I can know and I can calculate a lot of how will they react in different environments. So but that's shock response spectrum.
Yes, and I think it's more common than a question from Dirk Seckling. It's same for every measurement. If the user change, the results are no longer repeatable. They're only comparable.
Exactly. Yeah. So don't try to say, I hope I not use the word that this is the truth for an e-bike or for an electric car. This was in one situation with one driver, driving at different roads, but it's one sample. It's not the full one, and that's where you have to use your engineering judgment to when you compare to other ones. So it's a good point.
Yes, and I think that is the end of the questions and the comments, except that you're getting a lot of applauses.
Okay,
enjoy
thank you.
that. Thank you so much.
And just for the end here, you will get copy of this presentation I have shown here, and there will also be a recording of the webinar, so you can go back and see what did the man actually said. Okay. Thank you. Bye bye.